Hello everyone. Uh, so the purpose of this video is that I'm reading a book currently, and I just wanted to document that journey so that I can be more accountable. And that's the sole purpose of mine. Uh, let's get started. I have already read some of the pages of this book, so I'll just go through that once quickly, and then we'll start the session. Okay, and this is a very nice book, by the way. Modern Computer Vision with PyTorch. It has been recently released, probably a couple of months ago, the latest version, right? So previously, I have read about that there are some neural networks with adjust the weights until a learns a given task, and that task is called training the neural network. Okay. There were some generic things regarding neural networks which anyone would know if he or she has some knowledge about ML. Okay. So we have read this by me. I have read this. Okay, cool. So I was at uh, page number 22. Yep. Process by which is, yeah. So I was on this page. So let's get started. I was going to implement the gradient descent code, define the feed forward network, and calculate the mean squared error loss value as we did in this feed forward propagation in the code section. Okay, cool. Also, let me just open up its GitHub. I'll also code along this book, whatever code this book has. I'll also code that. For computer vision, PyTorch, GitHub, one, two. I guess I'm. So increase, I have implemented this already. Okay. Increase each weight and bias values by a very small amount and calculate the overall squared error loss value one at a time for each weight and bias updates. The following code, we are creating a function named update weights which performs gradient descent process to update weights. The input of the function are input variables to the network inputs, expected outputs, weights, which are randomly initialized at the start of the training of the model. Okay, that is quite obvious that uh, even today, I mean, for any neural network in the starting, or when we are training or pre-training the model, weights are initialized randomly, and the learning rate of the model, the learning rate is also, the inputs are this, the learning more on the learning rate and latest. Ensure that you deep copy the list of the weights. Okay, as the weights will be manipulated in later steps, deep copy ensures that we can work with multiple copies of weight without disturbing the original weight values. Okay, we'll create three copies of the original set of weights that were passed as an input to the function: original weight, temporary weight, and updated weights. Okay, cool. So they are doing this. Okay, uh, let me also code it up while I'm reading. Uh, yeah. Uh, eh, cool. Uh, have eight weights, puts, outputs, weights, learning weights. What the fuck? Okay, cool. Original weights. is equal to the copy temporary weights. Okay, we are making somewhat like e copies of the weights and weights. Cool. Now calculate the loss value, original loss, with the original set of weights by passing inputs, outputs, and original weights through feed forward function. Cool. So the original loss would be equal to feed forward, and here we have inputs. So same thing will go down here. Inputs, outputs, and weights. And now we'll loop through all the layers of the network. Okay. So for I comma layer in rate in original weights. Okay. Let me just quickly Google it up that what is enumerate. Or let's just chat GPT. I sometimes I wonder why they don't directly redirect it to chat GPT. I have to go to the AI page. Cool. So what is enumerate in Python? Let's just ask. The Python, it is a built-in function that will allow me to iterate over sequence while keeping the track of the index of each element. Okay. 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 Oh. Oh. So I think this example sums it up clearly that what is enumerate in Python. Okay. It just helps in indexing the elements on which we are iterating. Okay, so that is an improvement. That's it. Okay, cool. So for I comma layer in enumerate original weights, and we are just looping, and there are a total of four lists of parameters within our neural network. Two lists for weights and biases that connects the input to the hidden layer, and another two lists is for weight and bias parameter that connects the hidden layer. Okay, so for the context of viewer, I guess if you have not read this part, so we are implementing this neural network uh, in which our output is a continuous variable, and we have three hidden neurons, two input neurons, and one output neuron, right? Uh, uh, that's a pretty basic neural network, right? It's not even deep. If we would be having multiple hidden layers, then I'll call it a deep neural network, right? Cool. So let's jump back in where we were. Yeah. So there are a total four list of parameter, two for weights and biases that connects the input to the hidden layer, and the another two for the weights and bias parameters that connect the hidden layer to the output layer. Okay, cool. Now we loop through all the individual parameters, and because each list has a different shape, we leverage np.this to loop through each parameter within a given list. Okay, so yeah, ask what is well, this is a numpy similar to okay. Oh, okay. But it works specifically with numpy arrays and provides the index as a table for each element in a multi-dimensional array. Okay. Okay, cool. Let's say we have this 20, 30, 40. Okay, so this is a 2D array, and okay, yeah, uh, that sums it up here nicely. Okay, cool. Uh, uh, I've done this. We'll move through individual parameters, and because each list has a different shape, will leverage this to loop through each parameter within a given list. Okay, so for x comma y in np dot and age layer layer. Uh, Now we'll store the original set of weights in temporary weights. We select its index weight present in the ith layer and increase it by a small value. Finally, we compute the new loss with the new set of weights for the neural network. Okay, so here what we are doing is that we are saying that the temporary weights, let them be equal to, let me just first of all the temporary weights is equal to copy, and now the temporary weights, I'll change these weights, right? A comma, it's we are indexing it and we are just increasing it by a small value. What the fuck is this? This is a new variable and they have initialized it with an underscore. Okay, cos is equal to the forward. Okay, outputs, outputs, and temporary. Okay, and now I'll calculate the gradient plus minus original loss. Okay, I have calculated the original loss already. Yeah, so this minus this divided by this small change. Okay, so gradient is nothing but dy by dx. So we have just done this. Okay, finally the process of updating a parallel parameter by a very small amount and then calculating the gradient is equivalent to the process of differentiation. Okay, yeah. Finally, we update the parameter present in the corresponding ith layer and the index of the updated weight. So till here we have just calculated, we have here calculated the loss, we have calculated the gradient. Now we'll update our particular weight. Okay. Finally, we update the parameter present in the corresponding ith layer and index of the updated weights. The updated weight value will be reduced in proportional to the value of the gradient. Furthermore, instead of completely reducing it by a value equal to gradient value, we bring in a mechanism to build trust slowly by using the learning rate LR. So this is important. The updated weight value will be reduced. It will be reduced, but it will be reduced slowly. The learning rate. Okay. So this is important. Good. So now I'll say updated weights will be equal to uh, a gradient learning rate. Okay, so there is quite let me just complete this function. Once the parameter values across all layers and indices with layers are updated, we return the updated weight values as updated weights and the original logs. Cool. So I'll update it here. Return updated weights and original logs. Cool. Yeah. So so there is a convention, and I just wanted to clarify it for myself and for other people also, that this indicates that the variable or method is for internal use. Okay, getting my point. It is accessible to everyone, but it's just for the internal purposes. Okay, so if you can see here, this we don't want it to access or to get it returned anywhere. That's why the authors have used an underscore the start. Cool. One of the other parameters in the neural network is batch size, and considered in calculating the loss values. Okay. In the preceding scenario, we considered all data points to calculate the loss. However, in practice, when we have thousands or in some cases millions of data points, the incremental contribution of greater number of data points while calculating the loss value would follow the law of diminishing results, and hence we would be using a batch size that is much smaller compared to the number of data points we have. We'll apply gradient descent using one batch at a time until we exhaust all data points with one epoch of training. The typical batch size is considered in a building a model is anywhere between 32 and 1024. It's usually a power of 2, and for very large models, depending on the scenario, the batch size can be less than 32. Okay, cool. Implementing back propagation using the chain rule. So if you get stuck upon anywhere, I would say to you should check StatQuest. Okay, he has clearly explained all these topics. So okay, yeah. So far we have calculated gradients of loss concerning weight by updating the weight by a small amount and then calculating the difference between feed forward loss in the original scenario when the weight was unchanged and the feed forward loss after updating weights. One drawback of updating weight values in this manner is that when the network is large, okay, and we have more weights to update, a large number of computations are needed to calculate loss values, and in fact the computations are to be done twice, one where weight values are unchanged and again where weight values are updated by a small amount. This results in more computations and hence require more resources and times. Okay, and now we'll leverage the chain rule, which does not require us to manually compute loss values to come up with gradient of loss concerning the weight value. Okay. Hmm. Okay. Okay. So this section they'll only cover how to update the value of W11 using the chain rule. Okay, how to update this value using the chain rule. The same learning can be extended to all the weights and biases of the neural network. We encourage you to practice and apply chain rule calculation to the rest of the weights and bias values. Additionally, to keep this simple for our learning purposes, we will be working on only one data point where the input is this and the expected output is 0, right? Okay. Till now, what we have done, we have updated all our weights, okay, using this. But this would be quite computationally hectic to do, right? Good. So what do we do? We apply the chain rule. Yeah. Given that we are calculating the gradient of loss values with W11, let's understand all the intermediate components that are to be included while calculating the gradient through the following diagram. Okay, W11. Okay, so this comes into picture H11, A11, and Y head comes. That W11 is contributing to the loss value through a path that is highlighted. This path. Okay, the loss value of the network is represented as follows. The predicted output value Y is calculated as follows. Okay, there would be contribution of A13 and this to A11. Okay, good. So how we are getting this? We are getting this by A11 multiplied by W31 plus W32 multiplied by A12 plus W33 multiplied by A13. Okay, this is okay. Now we have formulated all the equations. Let's calculate the impact of change in the loss with respect to change in weight one W11 as follows. Okay, this is called chaining. Essentially, we are performing a chain of differentiations to fetch differentiation of R interest. Okay. 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 So what they have done is they have uh, used chain rule to calculate the impact of W11 on the loss. Okay. So basically, we want to update W1. So, and that is why all this has been done. Gradient descent, we perform the weight update process sequentially, one weight at a time. While leveraging chain root, we learned that there is an alternative way to calculate the impact of change in weight by a small amount on the loss value, however, with opportunity to perform computations in parallel. So, yes, this is important. Since we are updating parameters across all layers, the whole process of updating parameters can be parallelized. Furthermore, given that in a realistic scenario, there can exist millions of parameters across layers, performing the calculation for each parameter on a different core of GPU results in the time taken to update weights is much faster exercise than looping through each weight one at a time. Okay, cool. Now that we have a solid understanding of back propagation, both from an intuitive perspective and also by leveraging the chain rule, let's learn how feed forward and back propagation work together to arrive the optimal weight values. Forward and they work together. Okay. So we are now going to put this together. Okay. The input is connected to a hidden layer that has three nodes. The hidden layer is connected to output, which has one node. Okay. Now we'll create a network for the relevant packages. I have already initialized weights and bias values randomly. The hidden layer has three units in it, and each input node is connected to. There are six weights, and there's additionally connected to. Okay, so uh, upon looking this, this is like weights of the hidden layer, right? And yes, the weights of those three hidden layers, and then we have one bias vector, not bias, but then we have one not outputs values. We read the initialized hidden layer has three units in it. Okay, input node is connected to each hidden layer, hence there are total of six weights values and biases, one bias and two weights coming from two input nodes. Okay, okay, okay. Only one weight. The preceding code, the first array of parameters corresponds to the 2 cross 3 matrix of weights that connect the input layer to the hidden layer. Okay, okay, got it. The second array of parameters represent the bias values associated with each node of the hidden layer. Yeah, okay, cool, 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 cool. The third array of parameters corresponds to the 3 cross 1 matrix of weights joining the hidden layer to the output layer. This one. This 3 cross 1 matrix is this one. Right? The final array of parameters represents the bias associated with the output layer. Cool. Cool. Run the neural network through 100 epochs of feed-forward propagation and back propagation. The functions of which were already learned and defined as this functions in the previous sections. Okay, already done. Uh, okay, cool. Update the weights over 100 epochs. Have I done this? Yes. Yeah. So let's go through this process. This pop change loss is equal to eight eights x y 13 0.001 mostly 0.01 losses and okay so uh, here we have inputs, outputs, the weights and learning rate, right? Now let me also initialize weights. I have not defined what would be my starting random. We'll just copy paste it here because it makes no sense to write this. Okay. If you want, you can also do it. Right. Yeah, cool. Now what they are doing, they are saying they plot the loss function. Okay. So let me just go to matplotlib plot sp and now okay. So these are my input values. Taking so much output. Not different. Mm, Now it should be fine. IDX is not defined, but the okay. Oh, I've done a lot of mistakes. Okay, now it works fine. Right. Yeah. Cool. So now let's just plot the graph and lt dot plot losses and lt dot title. Let's just show this lt dot its label will be equal to the box lt dot y label will be cost value. So when we iterated from for 100, when we run 100 iterations, you can see that the loss tends towards zero, or it is nearly zero, right? That is a big thing. As you can see, the loss started at around 0.33. We check, yes, and steadily dropped to around this. This is an indication that weights are adjusted according to the input output data. And when an input is given, we can expect it to predict that we have been comparing it against in the loss function. Okay, now we can also print weights will be similar. Okay. Once we have updated weights, make the predictions for the input by passing the input through the network and calculate the output value. Okay. Now this is known as what I would say inferencing. Equal to np dot it's forward w0 plus w1 divided by Let's see whether it is close to zero or not. And hooray! It's very close to zero. Cool. The output of the preceding code is the value this, which is a value that is very close to the example of output. As we train for more epochs, the print out value gets even closer to zero. So far, we okay. Let's just uh, run it for 1,000 epochs. I have plenty of time. Uh, See, it's more and more nearer to zero. You can see, right? This is minus 4 into 10 to the power minus 1. Right? So, understanding the impact of the learning rate. In order to understand how the learning rate impacts, let me just squeeze it up a little bit. Yeah. In order to understand how learning rate impacts the training of a model, let's consider a very small, simple case in which we try to fit the following equation. Okay. Note that y is the output, x is input. With the set of inputs and expected output values, we will try to fit an equation with varying learning rates to understand the impact of the learning rate. Okay. Find feed forward function. Furthermore, in this instance, we will modify the network in such a way that we do not have a hidden layer and the architecture is as follows. So this is a simple equation. Note that in the preceding function, we are estimating parameters w and v. Okay. Okay. Define the update weights function just like we defined it. The gradient descent code section. Okay. Good. Weight value over increasing epoch when the learning rate is this. So after 200 epochs, it does not change much. It attains stability at this point. Okay. The desired value of weight is 3 because that's what this equation is telling us. Y is equal to 3x. It has attained that value, right? But it took around 200 iterations, approximately 200 or 150 iterations to reach at the value, right? The weight value gradually increased in the right direction and then saturated at this point. To understand the impact of the value of the learning rate on arriving at the optimal weight values, let's understand how the weight value varies over increasing epochs when the learning rate is this and when the learning rate is this. Okay, good. The following charts are obtained when we modify the corresponding learning rate value in step 5 and execute step 6. Okay, cool. So when the learning rate is 1 or when we just uh, do whatever that gradient says, we update our weight values blindly, then shit happens, right? And then when we update weight values with the learning rate of zero point 0.1, uh, it increases and reaches uh, very quickly. So let's just read more about it. And when the learning rate was very small, it took a very long time to reach at the optimal value, right? However, with a slightly higher learning rate, the weight value oscillated initially and then quickly saturated to the optimal value. Finally, when the learning rate was high, the weight value spiked to a very high value and was not able to reach the optimal value. So, this is an important line. The reason the weight value did not spike by large amount when the learning rate was slow is that it was restricted by an amount that was equal to the gradient multiplied by learning rate. And this value gradient into learning rate is very small because learning rate is small. Okay. When the however when learning rate is high, weight update was high, and after which the change in loss when the weight was updated by a small value was so small that the weight could not achieve the optimal value. Right. Okay. Checking whether we are currently working on it. Okay, so this is quite understandable. It's not that hard. Okay, so this is also important. At propagation, we decrease the loss value error by adjusting weights and action that reduces the overall loss. Furthermore, the magnitude of weight update is gradient times the learning rate. Process of feed forward propagation and back propagation is repeated until we achieve as minimal as loss as possible. This implies that at the end of training, the neural network has adjusted its weight statuses that it products the output that we wanted to predict. The preceding toy example after training, the updated networks will predict a value of 0 as output when 1 comma 1 is fed. But okay, cool. This chapter we understood the need for single network that performs both feature extraction and classification in a single shot before we learned about the architecture and various components of an ANN. Next, we learned about how to connect various layers of neural network before implementing feed-forward propagation to calculate the loss value corresponding to current weights of the network. We next implemented backprop to learn about the way to optimize weights to minimize the loss value and learn how learning rate plays a role in achieving optimal weights for a network. In addition, we implemented all the components of a network: feed forward, activation, loss, chain rule, gradient descent to update weights in the pie from scratch so that we can have a solid foundation. Okay, cool. Here we have applied only gradient descent, right? I'm not like of background. What are the various layers in the neural network? Feed forward, back propagation, feed input layers, hidden layers, and output layers. What is the output of a feed forward propagation? Uh, it predicts the predicted value uh, y hat, and the objective is of this is to get the desired value. Right? How is the loss function of a continuous dependent variable? Okay, so we have seen that continuous we use mean squared error, and in categorical we use y log y product. What is stochastic gradient descent? Pretty red. There's a back propagation red. The update of all weights across layers using chain rule. Which functions are used within each epoch of training a neural network? Forward, training, back propagation, and that thing. I don't know what will be the exact answer. Why is training a neural network on GPU faster than analyze? And what is the impact of learning rate and GPU works well with tensors? What is the impact of learning rate when training a neural network? Learning rate should be small, otherwise it might happen that you might never get the desired weight values of weight. What is the typical value of learning rate param? Uh, 10 to the power minus 3, 10 to the power minus 6. Right. Yeah. So finally, I have read chapter 1 and I'll now start reading chapter number 2. Ooh, but I'll start after some time. So that's it for this video.